y'all. So can I hold up this toy and have you see it? Anybody see it? It's a little circuit board. And a little light just went out. That, oh, I've been spotlighted, woo-wee. This is a board containing an accelerometer, pretty small, you can't hardly even see it, but it's on it's the top thing on this side. I'm a little less backwards here. And what it's doing is it's just similar to what the previous talk was about. It's basically a sleep until something wakes you up kind of acceleration sensor. And in this case, it is programmed for 1/10 of a G to wake up and to light the light. And so if I rotate the board 6 degrees, it's on, and it'll stay on until it doesn't see the stimulus anymore, or a certain amount of time passes, because we don't want to kill the battery. And I'll talk a little bit about the battery life stuff as well, but basically it's a detector of motion in any axis, and it has a, well, you'll see. So now I'm going to go back to the screen sharing jive here, which I'm now just like massively expertised. Come on, you, don't make a liar out of me. There we go. And see what happens. Ah, there you go. Okay, so that working?
Yep.
All right. I am no longer with Analog Devices. I am happily retired, but I was for quite a while. God, I don't know, 30 odd years. All right, so this is basically brainwashing. I'm merchandising the notion that analog circuit designers have a lot of fun. Well, some of them do. This used to be a talk about a recent product, but it is no longer recent. It was done many years ago now. Basically a 3-person team. And we find the analog stuff to be more interesting than the alternative. The device I'm going to talk about, I'm not going to talk about all of it, but just some aspects of it, is a little 3-axis 12-bit digital output accelerometer that runs on 4 microwatts, working its little butt off, and 0.6 microwatts while it's waiting around for something to happen. And it's about a factor of 100 less than the previous generation. And the cool part of it is you or they, depending on volume, can buy it for, last price I knew was 35 cents. So it's a bargain. So the board basically has a little, I bet you can see my cursor too, a little accelerometer on it, a big fat FET to drive the LED, and a little teeny 6-pin microprocessor, which is only used for startup. Everything else is done by the accelerometer. Oh, look, I've got another slide here that I found accidentally. Basically, it says that the board is looking for, it looks 6 times a second to see if anything's going on, and lights the light for a few seconds, goes back to sleep, blah, blah. And I've covered the rest of this, and it's a 0.1 G threshold, but it could be a lot lower than that. The resolution of that particular accelerometer is about a milli-G, but we'll get to that. So the battery on there, which is, you can't see it now, because it's there. It's a 2032 lithium battery, has a capacity of 225 milliamp hours, which means, given a 300 nanoamp accelerometer, that ought to last 85.6 years. As was previously pointed out, there is such a thing as self-discharge in batteries. And I noticed that this thing went dead in my kitchen in a quiet spot in about 3 years. So what the hey, at least we're ahead of the battery with the accelerometer. The idea, though, of course, is that in a lot of cases, you don't get much part of the battery capacity to take for the accelerometer. And also, it's usually the only thing that's running all the time. And in applications where you don't wake up the system until something happens, the accelerometer's got to be awake regardless. So, and also there's scavenge power, which was totally trendy a while ago. I don't know if anybody still does it. So where would you need a really low power accelerometer? Well, obviously the sports watch industry is built on them, and that was an early entrant. Pacemaker. Analog has got a policy that we do not put our products in life-critical applications. Regrettably, a new salesman in California didn't know this and called on St. Jude. Hey, what can we do for you guys? And they gave him a RFQ for an incredibly low power accelerometer, like 700 nanoamps. And you know, he didn't know any better. So we got to work with those guys for quite a while. As you can imagine, replacing a battery in a pacemaker is an ugly situation. It's to be avoided. It actually, the role of the accelerometer in that St. Jude pacemaker is not life critical. It's a comfort factors thing. It tailors the response to your activity level and things like that. So it kind of passes the policy, but it was really an accident. Another place you might want to use these is in moo monitors. You can see the tag on the cow here, and you can also tell by the expression that it's not too pleased to have that tag. What these tags do is they had especially in the mad cow days, there was a whole panic about mad cow disease, and they had to stop the cows and get them away from the herd. And you could do this by measuring the motion of the cow. You know, there's three levels. There's a normal cow, a cow with mad cow, and a dead cow. And the latter two cases are of interest in this situation. And then there's also temperature and a whole bunch of other measurements. So people have put these things on a field of cows, and I don't know how, and they have a LAN, and the big peer-to-peer LAN that sends all this data around, and they analyze it to figure out when an animal is not acting like an animal really ought to act. Now, what I want to know after that is just what happens. You know, now you know there's a sick one out there, and he's got an ID number 25 digits long. So does a helicopter show up with a hook on it? And do these guys have numbers on their backs so that the helicopter can find the right one to take out? I mean, no wonder they're mad. So I don't know if none of you were even born when The Prisoner was on the TV, but this is kind of reminiscent of that, where the big white bouncing ball comes out and scoops somebody up and carries them away. Terrifying. Here's another application. It's called elderly monitors. It's the iPhone and I can't get up thing, but I don't like to talk about it because I'm that old. Now, well, I'm not as old as this guy. He's 130 years old, but it's basically the same deal, except you don't need the helicopter. The Vitruvian man tips over on one axis or another, and a lightning bolt goes out to some cell tower, and next thing you know, help is on the way, Mr. McGillicuddy. But anyway, that's another low power sort of situation. This is a spooky one too, especially in Japan. They're touchy about gas and earthquakes. I wonder why. And the idea with this gas meter, which is equipped with a suitable accelerometer device, is you want to shut off the gas if the earthquake happens. Well, that's nice, but you really want the brake to be on the output side of the meter, or it doesn't do much good to shut off the gas. I don't know if anybody ever noticed that, but it does sell parts. Now, there's another application you wouldn't think of for a micropower accelerometer in a giant vehicle, or for that matter, in any vehicle. Tire pressure monitors, it turns out, have to run, of course, on batteries that are in the wheel because they can't be wired to the car battery, obviously. And since they take a lot more power than anything should really take, you need a way to only turn them on when they're possibly useful. So the scam with these things is that an accelerometer in there, it operates as a wake-up thing. If the wheels are turning, then it says, okay, I should be looking at the pressure, and it turns on the pressure monitors, and otherwise it does not. So that in that particular application, it's kind of a stove. It can take 1 to 5 microamps and still do the right battery life. I don't know what they do with accelerometers in an arrowhead, but I am told that they do. And here's a picture of something that purports to be that. So I always put it in the talks, even though I don't know what it is. And then there's the question of waking on motion, not just a low power accelerometer, but something that can wake up when it senses motion, even though it's basically nearly dead at the time, being mostly off. And that's a special application, which has proved to be very profitable too. Here's an example. You walk into a dark room where your massive television doodad system is, and you go to pick up the remote control and walk into the wall because it's dark in there. But you can't see the on button on the remote because it's dark in there. So in this case, you pick up the remote and somebody's clever accelerometer just lights up the display and all the buttons for you. Amazing. Same thing with art theft. You know, that piece of art could hang on the wall for year after year until somebody, some enterprising soul decides to steal it. And when he does, you want your little sensor to come to its senses and sound the alarm, which, as you can see in this case, has stirred the authorities into action. Door kick-in. We got inquiries from several well-known chains of motels and hotels that apparently this is an actual issue. I don't know that the people who kick them in look like this guy, but apparently things that will sit on the door year after year without requiring maintenance and sound the alarm if somebody does something outrageous is a big deal. The tricky part with that, of course, is people do slam doors and things like that. So the system has to be clever enough to know, to analyze the signal, as in the preceding talk there, to know what the content is. Otherwise, you don't know whether you're dealing with an aggressive individual or just a moron. So what's doing it? What's this all about? Basically, you put acceleration into a sensor, you put the sensor output into some electronics, and out comes a useful output of some sort. And what's in the electronics depends on the sensor and the output requirements both. And that's what we do. I did. Okay, so how you do it? It's a mass and a spring thing, as the previous talk indicated. You know, there's a reference frame of some sort, the package or the chip, the die, whatever. And as a mass mounted on a spring, actually several springs in the case of a multi-axis. And when the thing gets accelerated, as opposed to going at a constant velocity, then the spring stretches and the little pointer moves down the scale there, right? And you read the acceleration. Of course, there's no pointer. And as an old physics professor of mine used to say, it's just F equals ma. And if you do the math, you know, ma one way, spring constant the other way, it turns out that the scale factor is the square of the resonant frequency of the system, which is a really cool thing, especially when you're testing it, because you don't have to bash it around. And no, that spring doesn't stretch at constant velocity. Measure tilt with a thing like this, you're just projecting the gravity vector onto the sensitive axis, whatever it may be. In the case of our little demo board here, it's all axes. It isn't built like this with a little tubing in there. So it's a conceptual drawing, but basically it displaces and it doesn't know it isn't acceleration. So to measure the proof mass on our accelerometers, I say their accelerometers now, the output of the mass is, the position of the mass is detected by differential capacitors. Basically 2 plates astride a finger. And of course, there's lots of these in there, not just the one pair. But the idea is, as the mass moves toward or away from these differential capacitor plates, this is a little exaggerated, then you can detect the capacitance change and figure out that it must have moved. So if you're looking at a sort of an aerial view, cartoon view of the thing, there's differential capacitors on all sides, all 4 sides of the sensor, and the moving mass, silicon blob there, is actually the central, the common terminal for all the capacitors. And of course, the ones that are on opposite sides move the same way and they get connected in parallel. Not a big deal. There's some numbers on here though. Those capacitors, when all said and done, are in the femtofarads, and the motion is in single-digit femtofarads, and that's per G. We'll come to some of that. Oh, so here's the nuts of one finger. The mass in there, so-called mass, is 4.4 micrograms, and the little fingers are 100 microns long and a micron and change apart, and 8 microns thick. And there's 16 sets of these, 8 on each side of a big square. And you total the whole thing up and you get 160 femtofarads. It's kind of pathetic. So there's also Z motion, which is not done with fingers. It's just the planar sensor element itself being measured with respect to the package, the substrate. Actually, it's not a substrate. There's another magic layer in there, but that's the basic game. So there's 3 capacitors going on all told. And the fact that the vertical capacitor is not symmetrical mechanically, there's only a plate below and not above, causes endless trouble. But it doesn't cause that trouble for me anymore. Okay, so here's a sensor. You can see the fingers here, that the measurement capacitor is on all 4 sides. You can see also there's not very many sets of them. We'll get a little magnified view of that. And in the rest of the space are springs. We'll get to look at a spring in a moment. And this giant mass of this thing, if you could follow it all around, a good percentage of it is just mass. The fingers, the springs, and some stoppers and stuff are exceptions, but other than that is mass. The big art with these things is in making it not break. And that a lot of these features on it are about that. It's easy to overload it and have it do something regrettable. So looking at it a little more closely, here's a closer view where you can see the sense fingers. They're little teeny sets of capacitor fingers straddling little teeny elements that come from the big mass. And that's what it is, a nightmare really. And a spring. This spring is an incredible special spring. It's patented, but not by us. It was patented by the brother of a guy who did a lot of the MEMS work for us. And to have the exact same spring constant in two directions. I don't know that it does, but that's the claim. Somebody's making money on it. Okay, put some numbers on here. The mass was 2.4 micrograms. The threshold, when you're at the 0.1 G threshold, the sensor element, the so-called beam, has moved 2.4 nanometers. And that's for the 0.1 G in the demo. That changes the sense capacitors 0.2%. So now you have 0.3 femtofarads to detect to make that 0.1 G measurement. At the noise floor, we get down into the zeptofarads, and that brings up a subject that is, well, this one, I would recommend that there's no one in this group young enough to or old enough to know why this is a joke, but it is. And if you remember Harpo, Groucho, and Chico, you'd probably get a better grip on it. But actual powers of 10 you can get from the web are as seen here. Now, in the old days, and I refer to, my middle-aged years, we still only had microfarads when we were talking about picofarads because the pico hadn't been invented. And in 19 something or other, I don't know, I can't see the slide anymore, mid-90s when I was taking Doc Edgerton's class at MIT, the local Tektronix scope rep came in to show off their latest product. And he was the first guy I ever heard use the term picofarad, and I was snowed. That's incredible. Well, see how things work a few years later. Well, it's more than a few years, but some years later, we got the zeptofarads, which are what you need in the accelerometer business, because that's what we're measuring. And while the guy was there, he just tossed this off. He said, for any well-behaved system that isn't ringing, the bandwidth is 0.35 over the rise time. You would be amazed how well that works and the enormous variety of systems that it works on. It's just, so I just thought of it. Every time I think of him and the picofarad, I think of this thing. 10 to the 90 and 3 dB are incredibly well related over a huge range. This is, as I say down here, you're supposed to know that the Johnson noise is 0.13 nanovolts per root hour hertz. Everybody knows that, right? Or KT over C. You need to have these isms in your head. So at the 0.1 G threshold in question, as I said, we got a 0.3 femtofarad capacitance change, and the product can actually resolve 1,000 times lower than that, a milli-G. So at that point, we're detecting 24 picometers of motion, which is a 40th of an angstrom, for pity's sake, and 3 attofarads, or 18 ppm. So if you take the Tony IC fabrication processes of today, which have features down in the single and low tens of nanometers, the 362 accelerometer that you buy for 35 cents can measure displacements of its proof mass that are 1,000th of that. It's amazing how this stuff works. I take no responsibility for the fact that the sensors are that good. Oh, so, okay. And just to make things worse, there's a stray capacitor on the output that's inherent in the way the sensor is built, which is 500,000 times larger than the resolution. It does get bad. So the other things you have to worry about in a sensor like this are that it gets moved by any kind of charge anywhere. Obviously, static will do it. And all the voltages you apply to excite the sensor so you can get some signal to read out also move it. And so everything has to be balanced. The force is always attractive, regardless of what you think of it. And the 3 axes have 1 pin, so somehow you got to mux and demux to get everything out of there. So hopefully that's a hard enough challenge. So I would assume for the rest of these slides that we started with a normal everyday 160 microampere accelerometer. And all we have to do to make the St. Jude's people happy is to get it down by a factor of 100 or 2 or 3. And I'm not going to tell you a lot about how that's done because all these years later, ain't nobody else got it. So I'd like to keep that where it is. But this is the fun, is, you know, it's kind of a kick to do a thing that nobody can do. So I'm not going to show all of, well, there's a big picture of the accelerometer, you know, just looking at a normal one. There's a sensor, a set of capacitors, there's some excitation signals that drive the capacitors, and will somehow make AC outputs at the output of the sensor that correspond to the various displacements, all timed in accordance with the excitation patterns. And there's some provision for scaling that up. And then it gets demodulated against the sensor clock, so you get back the actual motion and not the modulated mess. And then it gets processed through a routine A to D digital filter, blah, blah. And there's some accessories. Not a big deal, but it does take 160 microamps and we only have 1.6. So as you can see, a lot of these things take 24 times that all by themselves. So what to do? First thing we did was a little re-architecting. The original design with the digital filter and all that jazz, it sounds very trendy, but it's also god-awful bad. The right way to do it is to do analog filtering, which you can do for 12 nanoamps per axis, believe it or not, and then use a much lower A to D converter and you get rid of the digital filter altogether and so forth. And at that point, you get down to, I can't even see it here because it's blocked on my screen, but you get a whole lot of improvement in power. The blue numbers here represent where you got, and you can see there's some pretty good multiples. And then you can reduce the clock speed because it's not going so fast anymore by a large factor. So you get some more green blocks, and now you're getting pretty happy. And then, well, all right, so what we got from those changes is about a factor of 2.5 out of the whole thing. And they're the harder part, but on the other hand, a miracle happens for the rest of it. So happens that the number of proprietary God almighty things in there is such that I can't tell you about the rest of them, but it accounts for the vast majority of the improvement. That's kind of terrible, huh? But I will talk about a couple of things. I'm not going to talk about anything unless this thing moves. Oh yeah, so anyway, you end up with 99% of the original power saved. And I can't tell you a lot about it because it's all proprietary and stuff, but I can show you some examples and you will see that it's kind of a fun gig, I hope. Or you could say, God, that's really terrible. Okay, so it's all about mentality. If you think it can be done, it can be done. If you don't, it can't. And most of the power is wasted in most normal things. And architecture turns out to be the key. Let's see. Okay, so here's a trivial example. In a single supply system, which everything is these days, you need some voltage in the middle, BDD over 2 kind of thing, so that could be what would be ground in a split supply system. It's 0. It's that spot. Come on, you. I know you can do this. There it is. Okay. So traditionally, you'd put a couple of resistors and you make a BDD over 2 out of it. On the other hand, when you think about it, those are huge resistors for an IC. Orders of magnitude larger than you would like. And in addition, even with those big values, this thing takes 6.7 microamps, which if you're shooting for 1.6 microamps for your whole product, you just know that's a loser. But here's a possible other way to do it. And a lot of people think this is good, but in fact, it's garbage. So you start with one cap charged up to VDD, in this case, 2 volts, and another cap that's shorted. Nifty. Then you separate the wires on them, so they're now sitting there with 2 volts and no volts respectively, and they're both capacitance C, and then blam, you connect them together, and what do you know? You now have, instead of 2 volts on one C, you have 1 volt on 2 Cs, charge being conserved. God, that's clever, but it's in fact a piece of junk. If you think about it and run it at reasonable rates and with reasonable sized parts and so forth, it takes 25 nanoamps. Now that's a whale of a lot better than the 6.7 microamps of the resistors, and it's also a whale of a lot smaller. But you know, really, can't you do better than that? Sure you can. How about this? Take two capacitors, equal voltages, just short them together. Stick them in series between VDD and ground. Each one gets VDD over 2, give or take, and put them in parallel again. And now you got VDD over 2. And you can keep doing the second and third steps forever, T1, T2, T1, T2. So basically, the voltage on the capacitors is always VDD over 2, which is another way of saying there is no energy consumed. And that's exactly what happens. So a couple of cool things. First of all, what I just said, the caps never change voltage. That's just good. The first step only happens once, then it happens. The rest of it happens forever. And the second thing is, even if the caps are very dissimilar, you still get VDD over 2. This is a law of nature. You get about a 0.5% or 1% voltage error for a 20% mismatch. So this is an IC designer's dream. And furthermore, it ignores the bottom plate strays, which plague every capacitor in an IC, typically bigger than the capacitor itself in value. But this thing, if you do the math, it turns out it doesn't really care. So you build this thing this way out of some switches and some capacitors, and you wind up with 3.6 nanoamps, which compared to the original 6.7 microamps for the resistive approach is better than a factor of 1,000. And it's also a available lot better than the other switch cap approach. So that's one way to do it. Oh, here's some statistics on the thing. Yeah, all right, it said what I just said, about 1,000 to 1. Not bad. Now, another example would be a two-pole filter, and you'll be relieved to know that it's my last example. In this case, we just look at a way you might want to anti-alias the input to an ADC, for example, a little miserable old two-pole filter. Here's a little miserable old two-pole filter that a lot of people like to use. It's got 4 switch caps in it, a couple of integrating caps, and a couple of op amps. And you can make pretty power-efficient op amps, a couple hundred nanoamps as shown here. But there is the fact that you can't really power cycle the op amps because the output of each one is in use most of the time. So you sort of have to put up with the 200 nanoamps. And what you really wanted was something to run on a nanoamp or two, not 400. So here's the old Salad and Key filter from the 1950s. Anybody here born before 1950? I don't think so. So this is a nifty little biquad filter, simple math, any fool could do it. And it has a couple of liabilities really, well, maybe really only one, which is that the output contains the offset of the amplifier VOS in there. And that's pretty rude. It turns out that in the course of getting rid of the offset, you can also get rid of all the power. By the way, notice it's already a winner compared to the other biquad filter that was shown because it only uses 1 op amp instead of 2, so you already got a factor of 2, but that's nothing. So here's a scary thing that you can actually do, and we do in the 362. You can take the output of this thing, since that's a unity gain follower, you can take the output ahead of the amplifier. That gets rid of the amplifier's offset in the output because it's not there anymore, but it does make for higher impedance output, so you want to be driving something buffered when you're using this, and that's the case with the ADC anyway. So I redrew it at the bottom so you can see the architecture now. And the kinky thing about it, as you can see, is the amplifier is driving a capacitor, so its offset is no longer visible anywhere. It's not just in the output, it's ain't nowhere. And then there's a question of why you'd bother with a whole op amp when you could use a simple little miserable FET. And it turns out that if you use this simple little miserable FET, you can save a factor of 4 or so right there in current because it hasn't got the rest of the op amp in it. It's got half the input stage. And also it's easy to correct the filter for the gain error of the follower, which is a very stable phenomenon. So you can do pretty well with this thing, but that's only the beginning. I noticed an observation in passing here. 100% of the current you spend on that source follower goes to reducing noise, which if you remember the axioms, reducing noise is one of the only uses of current, the only valid uses of current. And the other, in the op amp there, at most 100 of its 250 nanoamps goes into the input stage. And even at that, it has 4 times the noise because there's twice the devices and half the current each. which I go into in some detail here. You can you can email it for it. It is a fact that a source follower is 4 times as current effective as the first stage of an op amp, and the rest of the op amp's a total waste anyway. So now we have reduced the current a lot, but now to get further, we say, why put those resistors in there? Why not be real IC designers and put in a switch cap filter for a switch cap for each one to make the filter? It has a lot of good virtues that I won't go into here. This is a switch cap for all of you who've forgotten what a switch cap is or never knew. You take a capacitor and you toggle a switch back and forth, and in the input and output V1 and V2, it looks like a resistor in some kind of weird time domain way. So you can basically make the moral equivalent of a resistor in discrete time circumstances with a switch cap. And that's all we need to say about that. So let's replace the resistors in our little filter with switch caps. It's the same circuit. It just has switch caps where there used to be physical resistors. And notice the phasing of the switches. This turns out to be important. They're in on the ones, then they're out on the zeros. These are labeled by the clock. So they're going out, in, out, in, out, in. And there's a happy thing about that, which we'll get to in a moment. And it does work really well, by the way. All this lies right down in the math. And all the heresies that are in that don't count for beans. So here's the interesting part. When the switches are in the out position, the zeros, the follower isn't driving anything because the capacitor is open circuited, which means you don't need to run the follower. Furthermore, the duty cycle of a switch cap resistor can be really low because the charging instant for the capacitor is very quick when the switch lands on one position or the other. So you can use a really small duty cycle where it spends most of its time on 0 instead of 1, and that means the follower can be off almost all the time. And if you look inside of a 362, that's just what's there. So now we're down to, I don't know, a few nanoamps for the whole miserable filter on each of 3 axes. So whatever you do, you get a factor of 3 win just by simple little scams. So our voltage divider got down a factor of 2,000, and a pretty good filter to start with got down a factor somewhere between 80 and 400, depending on how you run it. So unless there's a power consuming load to drive, there's no legitimate use of current except to reduce noise. And it's a sort of a pun there. Every other use is parasitic. The other use of current, of course, is to charge parasitic capacitances so that signals can swing. But noise is it. That's what it's all about. You can't use physical resistors in a nanopower design because the currents aren't big enough to make any useful voltage across any practical resistor. So there's only one set of resistors in the 362, and it's to make a resistive bridge thermometer. That's kind of a cheat. And architecture is what makes accuracy. Everybody, the bipolar crowd years ago, remember bipolar transistors? You don't. But, a lot of people made their careers around, oh my God, these things are exponential law out of 4 orders of magnitude. You can always do better with FETs. Here's a circuit designer. She's now working for Apple. We had to say Acorn when I was working for Analog. Apple doesn't like its suppliers to be revealed, but it's no longer Acorn to me, it's Apple. And have a good time out there, Nami. This is the other guy, Yisun Chen. He disappeared. I don't know what he did. He left Analog and never heard from him again. Spooky. So here's some stuff that is probably relevant to the original presentation and more or less now, but analog designers are everywhere. The national power grid is an analog design. So let me see, is there anything here worth talking about? Well, only one thing. All the transistors in the 362 design that you saw there have obviously been massaged to death, all dozens of them. And in the digital world, things are different. Good God. I'm sort of glad not to be designing things like this, but I hope they have other computers to do it. So if you want to be an analog designer nowadays, you got to go work for an IC house. Ain't nobody else doing it, they're just buying it. And here's an example from a famous maker of iPhones. It's got our stuff all through it. I see they still sand the IDs off them. So if you really want to have some fun with this junk, the analog website will give them free for students. You can get a handful of accelerometers. They're cheap anyway. You can buy them from Adafruit for $1 on a board. Good to do. And, you know, when I was still interviewing people, that would have snowed me. Now I'm not, so my opinion doesn't matter. This is always my last slide in the talks I give at the tech conference and stuff. Just never follow. I stole it from Audi, but it's just so true. And all these things are true. But the last one there, you know, think about it. That's it for me.
That was wonderful, Jack. I loved your closing statement. It's wonderful to hear all these insights, knowing you for so many years, to hear some of the stories behind what you actually did. First, a couple of quick things. I teach the Sallen key filter in our sensors course, so people who have taken it know it. Still useful. And my teenage daughters are heavily into The Prisoner. I got them into it.
Right.
We've watched almost the whole series. It hasn't quite gone out of style, although their friends have never heard of it. So there's a generational gap.
Their friends' parents never heard of it.
That's true. Good. But I mean, one of the big takeaways here, there's so many takeaways in your talk, but you guys did this not with a magic bullet anywhere. There were a lot of hard work pulling the power down all over.
It's magic buckshot.
I mean, it's really going at it with looking at the whole system and refining every part.
That's called preparation, Joe.
We used to play with the piezo accelerometers and just use a nano power comparator to detect a threshold if it moved. And of course, with a piezo accelerometer, you don't need to excite the actual sensor. You guys do, but that's probably by no means the leading source of current draw. I mean, if you, let's say, went to a passive accelerometer, the other stuff probably still dominates, I guess.
It depends on which one you're talking about, but it is true that sensor excitation is still a reasonably sizable term in there.
Yeah, yeah. I mean, if you're in a gyro, you're stuck because it just takes power there, and you can't get around it without.
You know, it's a funny thing there. We had several micropower gyro things just burst up among us, but the management they went through like 6 or 7 managements in a few years, but none of them seemed to get it that that'd be a useful part. And of course it is. I mean, it would be God's own part, but for some reason we never did one. But in the gyros, you can do some impressively good things to reduce the power structurally.
Yeah, yeah.
At least we thought they were impressive.
Yeah, you still have to drive the resonator, but you can pull that power down different ways. Yeah.
It's definitely a different world, but resonator's the word. If you make that thing work for you, you can do pretty well.
Yep. Let's open up for questions. I'm sure any of you who are circuit or accelerometer fans must be bursting with something. So I don't see the hands here. You can just jump in if you have any questions. So go ahead. If anybody wants to grab the mic, we have Jack here.
With Anui.
I have a quick question. So I'm trying to get my head wrapped around the way you achieve mid-rail voltage. So you use 2 capacitors and you can switch between them being in parallel and in series. How do you dictate the switching? Is it some clock that's constantly switching them, or?
Yeah, it's just CMOS switches and a clock.
Oh, so it's that easy. Okay, thanks.
Yeah, trivial would be the term. And it's weird too. We'd never seen the series parallel one at the time we did it. Everybody did it by 2 volts here, no volts here, slam together and blam, and just the light went on one day that's really dumb.
Yeah. And do you see any artifacts in your signal from that switching?
No, especially not from the series parallel one, because literally nothing changes. There's an output cap that makes that holds the thing while it's doing its tricks, but no,
it's almost like a charge pumper voltage multiplier, same kind of idea where you stack the capacitors in a different way.
Yeah, but it's benign.
Do you adapt the clock frequency? You probably do. I mean, you can detect motion in these things very slowly, and you can change some of these. Or is the internal clock always running at the same clip?
You could do it, and we don't. The wake up is the state from which it wakes up when it's in sleep wake has been pretty well toned down. There's nothing unessential running, but it's the same old clock rate. It could be slowed down, yes.
Okay, the floor is open if anybody wants to jump in.
Yeah, this is a fascinating presentation. I'm curious, do you think in terms of like fundamental physics, how close are we to having optimized out like everything when it comes to an accelerometer? Like do you see how much more development work is there to do, or do you see any paradigm shifts in future designs for accelerometers? And where do you think the most interesting like MEMS work that you've been exposed to, where's the next like step change? Where's the future in your mind?
The thing that was on my mind before I bailed was that if you look at these analog intensive designs, they don't scale with process. So you're up against it. You get to a generation of technology where you're building 40 nanometer transistors and you can't use it. So it seemed to me that the fundamental thing that has to happen in that field is that totally different ways of using the sensor, or maybe different sensors, but at least different ways of using the sensor that will scale is going to be an imperative. Even if you're building individual products, that's true. But if you're getting your designs as IP built into somebody else's design, that's got, the whole thing's built out of tiny parts, it ain't going to happen if you can't scale. So to me, that was the biggest horizon message that I was seeing. The device, the sensors themselves, it's tricky. It's a lot of process technology involved there, obviously, but and it's not my expertise at all. But it did seem like it wasn't advancing rapidly, although it definitely did. There were much cleverer sensor designs being proposed. I never got to work with one. Oh.
So you can't just use feedback and things like that to compensate for design defects. I guess to a certain point, your leakage, your gains, all of those just put you into a different realm, and then you have to go to a totally different solution. You're saying as you start to.
I think if you're looking future, I think the neural net thing is interesting for these too, because you can build a complex of sensors that do different tricks, and ultimately it's going to integrate down to one small object that is better than a bat.
I just went to a great talk hosted actually by people doing these things elsewhere at MIT, where they are looking at memristor type components, right? So it's a sensory resistor that has memory and can process to some extent, but using battery technology for them. So you look at movements of protons, essentially hydrogen ions. You can actually begin to scale that down to a chip level, and it's a whole different device family altogether.
Yeah, that's radical.
Rich, yeah, I don't know if you remember Rich Fletcher. He was around in the early days when he started coming by the lab. Rich, go ahead. You're muted, Rich. We can't hear you.
Hi, sorry. Thanks, Jack, for the great talk. I just had a quick question. I've been using the ADXL 362 since it first came out. It's a great part. I was looking at maybe using, waiting for some of the successors of the 362, but I noticed that, due to industry wanting, much thinner form factors and so forth, the chip packages are no longer available. I was just wondering, are chip packages going away? For prototyping, will the MLF package still be available in the future?
I don't know. One of the tragic things that happened while I was there is that second fellow on the team there, Yitzhak, designed the 364, which was basically a 362-like device, but it was in a much smaller form factor because it was basically chip scale. There was no package. And everything in it electronically worked great, but they couldn't solve a packaging problem that it had making that package. And as a result, it died a horrible death. But that's where things are going to go, one way or another.
Any other? Go ahead, Fenzang. Was it you? No, I heard somebody.
I just asking if I had answered the question. Instead of actually answering it, I gave a horrible story.
Well, sure. Well, I hope analog will still continue supporting, prototypers and you know, academia. So there'll still be some parts still available for prototyping.
Yeah. Well, you know, the joy of all that work is that you're working with something big enough to see and possibly even touch. So that I think it'll be harder and harder to get things with leads, but other than that, I think it's all right. You know, once you know how to deal with things that don't have leads, and it'll be there for a while.
I was just trying to order from DigiKey some analog switches last night, ADG style switches. I wanted to get one with a really low arm resistance. The ones that have the lowest arm resistance you can't get in through hole, of course. It doesn't exist anymore for the new components. My students are really good at dealing with surface mount. I'm not so much. So I still want through hole.
Yeah.
There are ways to adapt it. You can get breakout boards and stuff. But
Yeah.
I think you're right. It's nice to hold something in your hands when you're prototyping.
Yeah, and not drop it.
You got to never see it again.
At least with the through-hole part, you can see it on the rug.
Also true. Although you step on it, you feel it more, unfortunately, if it lands the wrong way.
Yeah, that whole business is scary. I can't imagine where it's headed, but if you look at the level of integration that's possible nowadays and the packaging techniques that are available, it's surprising there are any other parts.
I see what you're talking about. What you said earlier too, taking the IP and put it on another chip, it's in a whole other way to scale where you don't get the separate discrete components. You do it all with modeling and then you just drop it down.
Yeah,
So
spooky.
Yeah, it is.
I think I got out in the nick of time.
Yeah, well, not as much fun, but fun in other ways, right? There's so many more things we can do.
Oh yeah. I'm using the parts now. I'm not making.
Any more, anyone else? Or are we good?
It's not a question, but rather a comment. I really enjoyed your talk. And because I myself is a chip designer, I work for Kioxia Corporation, which is formerly known as Toshiba Memory. I design flash memory microchips. Just the point you mentioned, which is analog design is more fun than digital. It's just that hits the point exactly. And I say that when it's about a chip design, analog signals are analog, digital signals are analog, and even DC power is analog because of the noise. So everything down there is all analog. And analog design is the only way to go with that.
Yeah, it's all analog if it's hard enough.